Quark entanglement. A groundbreaking discovery in physics, the discovery of quark entanglement marks one of the most significant scientific breakthroughs of 2024, fundamentally reshaping our understanding of the universe. Two of the smallest known particles, quarks, can be separated by vast distances, yet remain instantly connected. When one undergoes a change, the other reacts immediately, with no signal, no delay, and no physical link. Einstein famously described this phenomenon as spooky action at a distance. In 2024, scientists achieved a remarkable feat by proving that this strange connection extends beyond photons and electrons to quarks, the fundamental components of matter itself. Quarks are not only incredibly small, but also perpetually in motion, vibrating at incomprehensible speeds. They form protons, neutrons, and all matter in existence. Unlike physical building blocks, quarks never remain stationary, constantly interacting through the immense force that binds them together. Observing them has long been considered an immense challenge, comparable to capturing lightning in a bottle. However, in 2024, researchers at CERN's Large Hadron Collider successfully accomplished this task. Quantum entanglement has long been a fundamental principle of modern physics, describing a connection so deep that measuring one particle instantaneously reveals details about its entangled partner, regardless of the distance between them. While this phenomenon has been reliably observed in photons and electrons, which are relatively easy to manipulate, quarks present a far greater challenge due to their instability and brief existence. Detecting their entangled states was once thought nearly impossible. Through high-energy collisions at CERN, scientists produced pairs of top quarks, the heaviest and most unstable type. These particles exist only for fractions of a second before decaying into other forms. Yet during this fleeting moment, their quantum states were found to be entangled. This discovery is comparable to flipping two coins that normally land independently on heads or tails. If those coins were quantum entangled, knowing the outcome of one flip would immediately reveal the result of the other, even if separated by vast distances. This is precisely what was observed with quarks, two particles so deeply intertwined that measuring one instantly provided information about the other. Quarks never exist in isolation, always forming part of larger structures such as protons, neutrons, and atoms. Despite the surrounding chaos and complexity, their entangled state remained intact. This phenomenon resembles two perfectly synchronized dancers maintaining their routine even while being thrown through a storm. Quark entanglement extends beyond a scientific curiosity, serving as a gateway to revolutionary technologies. Quantum computers, ultra-secure communication systems, and potential methods for instant information transfer across vast distances all rely on advancements in the understanding of entanglement. The level of precision required to detect this phenomenon is extraordinary, as identifying entangled states amid the aftermath of high-energy particle collisions is akin to detecting synchronized heartbeats in the middle of an earthquake. Beyond technological implications, this discovery raises profound questions about the nature of reality. If quarks, the fundamental building blocks of matter, can exchange information instantaneously, the universe itself may be more interconnected than previously believed. The concept of distance may be an illusion, shaped by the limitations of human perception. The discovery of quark entanglement is not just a technical achievement, but a philosophical evidence of weakening. Dark energy. In 2024, scientists uncovered something extraordinary about dark energy, an invisible force that has shaped our universe for billions of years. This discovery isn't just a minor adjustment in our cosmic models, it's a potential rewrite of the universe's fate and our fundamental understanding of reality itself. To understand the weight of this discovery, it's important to start with the basics. About 25 years ago, astronomers made a groundbreaking realization. The universe isn't just expanding, it's accelerating. Picture marbles on an endlessly stretching rubber sheet. The force responsible for this acceleration was named dark energy, and it accounts for about 68% of the universe's total energy content. But here's the catch. Dark energy isn't something that can be seen, touched, or directly measured. It doesn't interact with light, matter, or anything familiar. Its existence was inferred through the behavior of galaxies billions of light years away. Fast forward to 2024, and astrophysicists using advanced telescopes and sky surveys began noticing subtle anomalies in the data. When mapping the motion and distribution of galaxies across vast stretches of time and space, they found that the rate of cosmic acceleration might not be perfectly constant. It's as if dark energy, once assumed to be an unchanging cosmic force, is starting to waver. At first glance, this might sound like a minor adjustment, a footnote in astrophysics. But in reality, it's a seismic shift. The standard model of cosmology, the mathematical blueprint relied on to understand the universe, assumes that dark energy is a constant force. If this force is changing, it means something fundamental about how the universe operates has been missed. If dark energy remains constant, the universe will continue expanding forever, growing colder, darker, and emptier, a scenario often called the Big Freeze. But if dark energy is weakening, other futures become possible. The universe might slow its expansion and settle into a more stable state. Or, in a dramatic twist, gravity could regain dominance, pulling everything back together in a catastrophic event known as the Big Crunch, a mirror image of the Big Bang. Before rewriting the textbooks, however, scientists need absolute certainty. Measuring dark energy is like trying to detect the faint tug of a ghost on the largest structures of the cosmos. Researchers rely on tools like Type Ia, supernovae, cosmic microwave background radiation, and the distribution of galaxies across the sky. In 2024, next-generation sky surveys, such as those conducted by the Vera C. Rubin Observatory, delivered data with unprecedented precision. While not definitive proof, the results were compelling. Dark energy might not be constant after all. This discovery raises deep and unsettling questions. What exactly is dark energy? Is it a static force, or could it be a dynamic field, an invisible ocean of energy that ebbs and flows across cosmic time? Could it point to entirely new laws of physics that transcend current understanding? And if dark energy is changing, what does that mean for the universe's ultimate fate? These aren't just scientific questions, they're philosophical ones. They force a confrontation with the vastness of what remains unknown. The weakening of dark energy hints at a universe that isn't static or predictable, but fluid, dynamic, and still capable of surprises. At this moment, the edge of a new frontier has been reached. The data is tantalizing, the questions are profound, and the implications are staggering. What happens next depends on what scientists uncover in the coming years, whether dark energy continues to weaken, stabilizes, or behaves in an entirely unforeseen way. One thing is certain, this discovery isn't just a scientific milestone. It's a reminder of how much mystery still surrounds us. The universe isn't a finished story, it's a narrative still being written. And dark energy might just be the plot twist no one saw coming. So the next time you look up at the night sky, remember this: every star, every galaxy, every cosmic void is part of a vast, interconnected tale. And somewhere in that story, dark energy is quietly rewriting the ending. The first coherent picture of an atomic nucleus. Physicists have created the first coherent picture of an atomic nucleus. This is not merely a technical milestone. It's a profound glimpse into the hidden architecture of reality itself, a revelation about the very fabric of matter. At the heart of every atom lies a nucleus, a dense cluster of protons and neutrons bound together by the unimaginably powerful, strong nuclear force. For decades, scientists have struggled to understand this chaotic, miniature universe. Textbooks often show tidy diagrams of protons and neutrons arranged neatly like billiard balls packed together. But in reality, the nucleus is a swirling storm of energy and particles in ceaseless motion, a dynamic chaos that defies our everyday intuition. For nearly a century, physicists relied on two dominant models to study the nucleus. The shell model envisioned nucleons, protons and neutrons, arranged in energy layers, similar to how electrons orbit an atomic nucleus. Meanwhile, the liquid drop model viewed nucleons as particles suspended in a vibrating fluid-like state. Each model captured valuable pieces of the puzzle, but neither offered a complete picture. They were like two people describing an elephant, one focused on its trunk, the other on its tail. In 2024, something changed. Scientists managed to merge these two competing models into a single, unified framework. Using cutting-edge computational simulations and incredibly precise experimental data from particle accelerators, researchers created a coherent, dynamic image of the nucleus, one that captures both its structured stability and its chaotic fluidity. Think of it like photographing a tornado. A still image might show you the tornado's shape, but it would fail to capture the swirling winds that define its essence. Physicists in 2024 achieved the equivalent of capturing both the structure and the motion of the atomic nucleus in one breathtaking snapshot. They revealed not just where protons and neutrons are, but how they move, interact, and contribute to the nucleus's energy state. But why does this matter? Why should we care about understanding something so tiny that billions of nuclei could fit on the tip of a needle? First, this discovery has practical applications. With a clearer understanding of nuclear behavior, we could design safer and more efficient nuclear reactors. In medicine, treatments like proton beam therapy could be fine-tuned for unprecedented precision, improving outcomes for cancer patients. The applications extend into fields like material science, where nuclear properties influence everything from semiconductors to advanced alloys. Beyond the practical benefits lies something even more profound. The atomic nucleus is the battleground of the universe's fundamental forces. The strong nuclear force binds protons and neutrons together. The electromagnetic force repels positively charged protons, and the weak nuclear force drives radioactive decay. It's a tiny arena where the rules of reality are written, tested, and sometimes broken. By understanding the nucleus, we're peering into one of nature's most enigmatic theaters. And then there's the paradox of scale. Nuclei are unimaginably small, yet they contain nearly all of an atom's mass. This astonishing concentration of energy and matter speaks to something deeply counterintuitive about our universe, that vast power and profound complexity can be hidden within the tiniest spaces. It's a reminder that the universe isn't simply a collection of particles. It's a tapestry woven from relationships, patterns, and interactions. What's even more exciting is that this discovery may not be the end of the story. Instead, it feels like the beginning of a new chapter. Could the patterns observed in atomic nuclei also exist in extreme environments, like neutron stars, where matter is packed to near infinite density. Could this knowledge bring us closer to unlocking the mystery of dark matter, the invisible force that shapes galaxies and holds the universe together? In many ways, this achievement feels like humanity has finally put on the right pair of glasses. For the first time, we can see the atomic nucleus not as a blurry chaos of swirling particles, but as a dynamic, interconnected system governed by underlying order. And perhaps this is the greatest revelation of all, that even in the smallest corners of existence, in spaces so tiny they evade direct observation, there is elegance, structure, and beauty that transcends scale. The creation of the first coherent picture of an atomic nucleus isn't just a technical victory, it's a profound reminder that the universe, no matter how chaotic it seems, is built upon a foundation of order. It tells us that even the smallest building blocks of reality hold secrets grand enough to reshape our understanding of everything. Discovery of a super solid. Imagine holding. Discovery of super solid. Imagine holding a material in your hands that feels as rigid and structured as a diamond, yet flows effortlessly like liquid helium. It sounds like a contradiction, something pulled straight out of science fiction. But in 2024, physicists confirmed the existence of this mind-bending state of matter, a supersolid. This discovery isn't just another breakthrough. It's a glimpse into a reality where the ordinary rules of physics seem to dissolve, revealing a universe that operates on principles far stranger than we ever imagined. To understand why the supersolid is such a groundbreaking discovery, we need to explore two key ideas: solids and superfluids. A solid is defined by its atomic structure. Its atoms are locked in place, arranged in an orderly, repeating pattern, stable, rigid, predictable. A superfluid, on the other hand, flows without resistance, slipping effortlessly through tiny cracks, climbing up walls, and even defying gravity. It's almost ghostly in its behavior. These two states seem fundamentally incompatible, like trying to freeze water and boil it at the same time. But at the microscopic scale of quantum mechanics, such contradictions aren't just possible, they're inevitable. In 2024, scientists managed to create and study a supersolid directly in a laboratory using ultra-cold atoms cooled to just above absolute zero. At temperatures this extreme, the rules of classical physics break down. Particles stop acting as individual entities and instead behave as one cohesive quantum wave. But what happened next defied our expectations. The atoms settled into a crystalline grid, maintaining the rigid structure of a solid but simultaneously exhibiting superfluid behavior, flowing effortlessly across the lattice with zero resistance. It's as if you had a block of ice that allowed water to flow freely through its structure without melting or disrupting its solid form. This paradox, this impossible coexistence, was no longer theoretical. It was observed, measured, real. At first glance, the supersolid might seem like an esoteric curiosity, a strange quantum trick with little relevance to everyday life. But discoveries like these often lead to technological revolutions. For one, supersolids challenge our understanding of phase transitions, the processes where matter shifts between solid, liquid, and gas states. Traditionally, we think of these transitions as clear steps, each with defined properties. But the supersolid shows us that nature doesn't always respect these clean divisions. It suggests a hidden fluidity in how matter behaves, a blending of properties we thought were mutually exclusive. From a practical standpoint, supersolids could one day revolutionize fields like precision measurement, quantum computing, and materials science. Their unique combination of rigidity and zero-resistance flow could enable ultra-sensitive sensors, allowing us to detect gravitational waves with greater accuracy or engineer materials with properties we've never seen before. But beyond potential applications, Supersolids also tell us something far deeper about the universe itself. They reveal that the categories we use to understand reality, solid, liquid, gas, are merely approximations, convenient boxes we've created. But the universe refuses to be confined by them. This discovery isn't just about one exotic state of matter, it's about what it represents. It hints at the possibility of supersolids existing naturally in the universe. Could they form deep inside neutron stars, where matter is squeezed to unimaginable densities? Could they exist in the extreme gravitational landscapes of black holes? These are not just speculative questions. They are new frontiers waiting to be explored. At its core, the supersolid discovery underscores one undeniable truth. Quantum mechanics isn't just a set of abstract theories. It's the hidden blueprint of our universe. And every time we peel back a layer, we're confronted with something that feels impossibly strange, yet undeniably real. But there's another layer to this story, a paradox that extends beyond the lab. The more we understand about the supersolid, the more we realize how little we understand about the fabric of reality itself. Each breakthrough answers one question, but opens the door to 10 more. How do particles simultaneously exhibit order and fluidity? Are there deeper laws governing these behaviors that we've yet to uncover? And perhaps the most tantalizing question of all, what else is out there waiting to be discovered in the quantum shadows? The confirmation of the supersolid isn't just a scientific achievement. It's a reminder of how deeply mysterious our universe remains. It challenges our assumptions, rewrites our textbooks, and pushes the boundaries of what we thought was possible. But more importantly, it gives us a glimpse into a world where paradoxes aren't problems, they're pathways to understanding. As physicist Kantani